In this video, I'll define what a forest is, and we'll prove corollary 3.16, which says the size of a forest of order n having k components is n minus k. So what's a forest? Well, it's just an acyclic graph. So that is, every tree is a forest, but not every forest is necessarily a tree, right? A forest that is also connected is a tree. So samples of forests, if I say put these two trees together, this would be an example of a forest, or something like, right? We could have a lot of different components. As long as each component is a tree, then the graph is a forest. So every component of a forest is a tree. Now, we can use the previous theorem, which gives us the size of a tree, to conclude the size of a forest. So let's prove this one. Let G be a forest of order n and k components. Then what's our picture? We have, say, G1, G2, G3, and up to, we have k total components up to gk. Each one is a tree. So say G1, G2, up through gk are the components of G. Each, let's say the order of Gi is, let's call it n sub I. In particular, the sum of the n sub i's from I equals 1 to k is equal to n. And if I add up the sizes, G as ni, let's also give variables for the sizes. The size of Gi is m sub I. I should say let, since I'm declaring these as m sub I. In particular, the sum of the sizes of these components is m, and k components in size m. So m sub I, since each component is a tree, m sub I is equal to n sub I minus 1. Hence, m, which is the sum of all the m sub i's, is equal to the sum of n sub I minus 1 from I equals 1 to k. I can break this sum down. This is the sum from I equals 1 to k of the n sub I, minus the sum from I equals 1 to k of 1. So I just add up 1 k times, so that's just k. And if I add up the n sub i's, I get the order. So this is n minus k. And that proves this corollary. Okay, so that's another quick video for you. The size of every forest with k components is n minus k.